demos look flawless in a sandbox. You type a prompt and receive a perfect response. But the moment you deploy that same model into a multi-step enterprise workflow, like a messy 10-deep forwarded email thread, the perfection breaks down. Amnesia is the silent, expensive failure mode of production AI. It costs more than hallucination. Context evaporates, continuity snaps, and the assistant that was deep in the weeds yesterday suddenly wakes up with a blank slate. Users react to this amnesia by patching the gap with manual labor. They re-explain previous steps, paste screenshots of past decisions, and effectively become the database themselves just to reconstruct the world for the model. Prompt engineering and larger context windows fail to solve this by week 3 of production. The context window eventually fills with irrelevant narration, token budgets explode, and the system begins to drift away from the core task. A reliable architecture treats the large language model, or LLM, as a stateless compute layer. An LLM is a probabilistic model that predicts the next token in a sequence. It has no inherent memory. Continuity must exist entirely outside the conversation. True resilience requires abandoning the smart agent paradigm. You must wrap the probabilistic model in a strict, deterministic shell that anchors the truth in persistent infrastructure. Building that shell begins by assuming your data is hostile. In a forwarded email, a recruiter's signature often looks more extractable than the actual candidate's details buried in the body. Feeding a raw payload directly to a model results in a confident extraction anchored to the wrong person. The model solves the extraction problem, but fails the identity attribution problem. A deterministic intake gate strips null bytes and normalizes formatting before a single token is spent. These diagnostic gates isolate the identity boundary. By detecting forward markers and signatures, the system defines what is eligible for extraction before the model reads it. This pre-processing layer fails loudly and observably. It either identifies the boundary correctly or it doesn't. Whereas a contaminated model extraction fails completely quietly and slowly corrupts the entire system of record with perfectly formatted but illegitimate data. Deterministic gates reduce the number of plausible truths a model can see. System architecture, not prompting, dictates extraction accuracy. Convention suggests setting an extraction model's temperature to 0 for predictable deterministic output. Temperature is a hyperparameter that controls the randomness of the model's next token predictions. At temperature 0, a model becomes overly conservative with messy enterprise data. It often omits fields that are partially occluded or irregularly formatted, leading to silent data loss of critical but weak signals. Counterintuitively, enterprise reliability actually increases when you turn the dial and set temperature to 1 to optimize for maximum recall. The model acts as a generous stenographer, proposing candidates for every possible field instead of going blank. This high-variance extraction flows into an external research node and then hits a rigid validation layer written in deterministic code. The system treats the model's output as candidates, not as truth. Blunt validation rules automatically reject extracted job titles that exceed 60 characters or contain full sentence boundaries. No model is required for this step. The code simply enforces the domain boundary. Recall belongs to the probabilistic model, but absolute precision belongs to the deterministic validation code. Relying on multiple external APIs for data enrichment creates a collision problem. Merging their responses sequentially will eventually overwrite accurate facts with lower quality guesses. An enrichment cascade assigns data sources strict numeric priorities. Web scrapes operate at priority 5, while a generic area code approximation sits at 0. Tracking per-field provenance ensures lower priority sources can fill blanks, but never stomp values claimed by more authoritative sources. This discipline is essential for syncing with a customer relationship management system, or CRM. Standard API documentation is often a suggestion. Custom views frequently ignore requested parameters or truncate data unexpectedly. Instead of manual mapping, the system auto-generates schemas directly from the CRM API. It then uses a SHA-256 hash, a unique digital fingerprint, to incrementally sync only the records that have meaningfully changed, rather than reprocessing the entire database. Per-field provenance and strict sync normalization turn external data integration from a dangerous gamble into a controlled accumulation of truth. Coordinating asynchronous tasks using abstract AI agent frameworks often leads to race conditions. If a worker dies mid-flight without clear state management, you end up with duplicate emails or corrupted records. Classical concurrency provides the cure. The Postgres skip locked command lets one worker secure a row while forcing others to cleanly bypass it for the next task. State columns like claim tokens turn the queue into a ledger, making stale recovery deterministic. This resilience continues at the cache layer. A circuit breaker monitors the health of a memory store like Redis. If it fails, the system safely bypasses the cache and continues processing, ensuring that a transient wobble doesn't cascade into an outage. On the front end, this state is recovered through a mandatory session boot protocol. The AI is structurally forbidden from answering until it queries the task database and loads the session handoff files needed to reconstruct its world. Resilience is built on rigid database locks, optional caching, and mandatory state recovery protocols. Delivering these results to a user reveals a final friction point. No single search index fits every data shape. Structured CRM data, conversational transcripts, and live records require different backends. A unified search router dispatches queries based on deterministic keyword rules. It sends equipment searches to Azure AI for structured ranking, while routing meeting notes to Postgres Vector for semantic similarity. During a live call or screen share, the raw chain of thought text from a model is visual noise. It competes with the user's momentum and exposes internal reasoning that should remain hidden. Dual-channel streaming splits the model's output into two paths. The internal reasoning routes to a hidden panel for operators, while parallel tool call results arrive as structured JSON events, a standard data interchange format, to render clean UI cards in the foreground. To protect sensitive identities, a runtime privacy toggle dynamically maps firm names to generic industry labels right before rendering. This preserves the decision-critical structure without the risk of a second diverging index. The presentation layer must insulate the user from the model's raw processing. Routing, streaming, and runtime toggles separate the reasoning from the results. The model is merely the engine. This blueprint of indicate gates, validators, database locks, and routers provides the chassis that keeps the system on the road. True enterprise reliability comes from treating memory as infrastructure and raw text as an untrusted input requiring deterministic gates. Deploying feature flags as hard-coded kill switches protects user trust by preventing experimental or momentum-blocking behaviors from disrupting real-world workflows. While the probabilistic model raises the floor of what is possible, the deterministic architecture built by the engineer remains the ceiling for enterprise reliability.